Have you ever wondered what keeps a bridge from collapsing under the weight of heavy vehicles, or how a skyscraper withstands high-speed winds? The answers lie in the mechanics of materials. Welcome to the captivating universe of mechanics of materials, a fundamental area of study within the realm of mechanical engineering. This fascinating discipline plays a crucial role in our daily lives, from the design of the chair you're sitting on, to the car you drive, the building you live in, and even the smartphone you're holding. Mechanics of materials, sometimes referred to as strength of materials, is the branch of engineering that deals with the behavior of solid objects subjected to various types of force. It's a world that goes beyond the surface, delving deep into the internal reactions and deformations that occur when materials are put under stress. At the heart of mechanics of materials lie three fundamental concepts: stress, strain, and modulus of elasticity. Stress is the internal resistance offered by a material to an external force. Imagine a rubber band being stretched. The tension within it is an example of stress. Strain, on the other hand, is the deformation caused by stress. In the case of the rubber band, the stretching represents strain. Modulus of elasticity, also known as Young's modulus, is a measure of how a material will deform under stress. It's a bit like the springiness of the rubber band, how much it stretches under a certain amount of force. Understanding these concepts is vital in designing and building structures that can withstand the forces they're subjected to. From bridges that bear the weight of countless cars, to skyscrapers that resist the power of gale-force winds, and aircraft that endure the stresses of flight. All these marvels of engineering are testament to the power of mechanics of materials. Next, we dive deeper into the world of stresses. Stress, in the context of mechanics, is not something to worry about, but rather to understand. Now, we aren't talking about the kind of stress that makes you want to pull your hair out. Nope. In the field of mechanics, stress is a measure of the internal forces that develop within a material when external forces are applied to it. Imagine you're trying to stretch a rubber band. The force you apply to pull the ends of the band apart results in a certain kind of stress called tensile stress. This is the stress experienced by a material when it's being pulled apart or stretched. Like the rubber band, materials under tensile stress tend to elongate. Now let's consider the opposite scenario. Suppose you're pushing the ends of a spring towards each other. The spring is now under what we call compressive stress. This is the stress experienced by a material when it's being squeezed or compressed. Unlike tensile stress, materials under compressive stress tend to shorten. Finally, we have shear stress. Picture yourself trying to cut a block of cheese with a knife. The force you apply with the knife is parallel to the surface of the cheese. This causes the cheese to deform along the direction of the force, resulting in shear stress. So, to recap, we have three types of stress: tensile stress, which causes a material to stretch; compressive stress, which causes a material to compress; and shear stress, which causes a material to deform along the force. Each of these stress types plays a vital role in the design and analysis of structures and materials. As you can see, stress in mechanics isn't about panic or anxiety. It's about understanding how materials respond to different forces. It's about using this understanding to create structures that can withstand the test of time and pressure. Now that we have a grip on stress, let's move on to its partner in crime, strain. When materials are stressed, they strain. But what does that mean exactly? Well, imagine you're kneading a piece of dough. As you push and pull, the dough stretches and deforms. That's strain. It's the measure of deformation representing the displacement between particles in a material body. Let's break this down a bit further. Strain is a dimensionless quantity, meaning it has no units. It's simply a ratio of how much a material deforms to its original size. Think of it as a percentage of change. If a metal rod stretches by 1% of its original length, we say it has a strain of 1%. Simple, right? Now, strain can be either tensile or compressive. Tensile strain happens when a material is pulled apart, causing it to elongate. Imagine pulling a piece of bubble gum apart. That's tensile strain. On the other hand, compressive strain happens when a material is pushed together, causing it to shorten. Think of squishing a marshmallow, that's compressive strain. There's also a third type of strain called shear strain, which happens when a material is twisted or experiences a sliding force. It's like wringing out a wet towel. The fibers in the towel slide past each other, causing the towel to deform. So, in a nutshell, strain is all about how a material responds to stress. It's like the material's way of saying, hey, I'm feeling the pressure here, but here's the catch. Not all materials strain the same way under the same stress. Some materials, like rubber, can strain a lot before they break, while others, like glass, can hardly strain at all. This variation in strain response is what makes studying the mechanics of materials so fascinating. It's a bit like people, really. We all respond to stress differently, don't we? So, in a way, studying strain is a bit like getting to know the personality of a material. With stress and strain explained, let's combine them to understand the concept of modulus of elasticity. Modulus of elasticity, a fancy term, but an even more fascinating concept. Now, what do we mean by this? In a nutshell, the modulus of elasticity, also known as the elastic modulus, is a measure of a material's ability to withstand deformation under stress. It's the bridge that connects stress and strain, two fundamental concepts in the mechanics of materials. Let's break it down a bit. Picture a bridge with heavy traffic. The weight of the vehicles is the stress, the bending and flexing of the bridge is the strain, and the bridge's ability to handle this pressure without collapsing. That's the modulus of elasticity. Now, why is this so significant, you ask? Well, the elastic modulus is key to understanding and predicting how a material will behave under different stresses. It's like a material's unique fingerprint telling us whether it's brittle, ductile, or tough. Brittle materials like glass or ceramics have a high modulus of elasticity. They can withstand a lot of stress, but they're not very flexible. They tend to break suddenly without much warning. On the other hand, ductile materials like gold or copper have a lower modulus. They're more flexible and can be stretched or shaped without breaking. And then there's toughness, the ability of a material to absorb energy and deform without fracturing. A material like rubber might not be very stiff, but it's tough because it can absorb a lot of energy before it breaks. So in essence, the modulus of elasticity gives us a way to quantify and compare these different properties. It's a vital tool for engineers, helping them choose the right materials for the right applications. Whether they're designing bridges, buildings, or even spacecraft, understanding the modulus of elasticity is crucial. With these fundamentals in place, let's put them to use. And remember, like any good engineer, it's not just about knowing the theory, but also about applying it in the real world. Stay curious, keep exploring, and let's discover more about the fascinating world of the mechanics of materials together. The theories of stress, strain, and elasticity aren't just for textbooks, they shape the world around us. Let's take a moment to appreciate the marvel of engineering we live in, where these mechanics of materials principles are elegantly applied. We'll kick off with bridges, the epitome of strength and endurance. The Golden Gate Bridge, for instance, gracefully stands against the test of time and weather thanks to the principles of stress and strain. Engineers calculated the stress each cable would undergo, ensuring the strain was within the material's elastic limit. This careful planning prevents permanent deformation, ensuring that the bridge can hold up cars, people, and even face strong winds without buckling or snapping. And it's not just bridges. Skyscrapers, those towering symbols of human achievement, are another great example. Take the Burj Khalifa, the tallest building in the world. It's designed to withstand the forces of nature, from wind loads to seismic activity. The mechanics of materials helps us understand how materials behave under these stresses and strains, allowing engineers to design structures that can resist these forces without failing. But the applications don't stop at megastructures. Even our everyday machines owe their efficiency and longevity to these principles. Consider an airplane engine. It has to endure extreme temperature changes and high pressure, all while maintaining peak performance. By understanding the stress-strain relationship and the material's elasticity, engineers can design engines that stand up to these challenges. And let's not forget about biomedical applications. From designing prosthetics to understanding bone mechanics, the principles of stress, strain, and elasticity provide valuable insights. These principles help create prosthetics that mimic the natural movement of limbs, giving amputees a better quality of life. So, You see, these principles aren't just academic theories, they are the bedrock of modern engineering. They help us push the boundaries of what's possible, creating safer, more efficient, and innovative structures. To sum up, the mechanics of materials is not just a subject, it's the science behind our safe and innovative structures. The mechanics of materials, a complex subject, but hopefully we've made it a bit simpler for you. Let's take a moment to recap what we've covered in this journey through the foundation of mechanical engineering. We started with stress, the internal resistance of a body to external loads. It's the pressure that materials feel when they're put to use, and it's crucial in determining whether a structure can withstand the loads it's expected to bear. Stress is everywhere, from the weight of a skyscraper bearing down on its foundation to the tension in a guitar string. Then we moved on to strain, which is the deformation of materials under the influence of stress. When stress acts on a body, it changes shape, and this change is what we call strain. Just as stress is a measure of the internal force, strain is a measure of the resulting deformation. We bridge the gap between stress and strain with the modulus of elasticity. This is the material's ability to return to its original shape after being deformed. The modulus tells us how much a material will deform under a given load, and it's vital in the design of safe and efficient structures. It's the bounce back in a trampoline, the flex in a diving board, the give in a skyscraper swaying in the wind. Finally, we looked at the real-world applications of these concepts in engineering. From the design of bridges and buildings to the manufacture of everyday items, the mechanics of materials is at work. It's the science behind the structures we depend on every day. Remember, the mechanics of materials is the hidden hero behind every stable structure you see. It's an intricate dance of forces and reactions, of stress and strain, and of resilience in the face of loads. Understanding it is key to unlocking a world of engineering possibilities. So keep exploring, keep learning, and keep building. The world is full of structures, waiting for you to understand them. Today, we've embarked on a journey through the mechanics of materials, unearthing the science behind our everyday structures. We've delved into the fascinating world of stress, strain, and the modulus of elasticity, piecing together the puzzle that forms the foundation of mechanical engineering. Our exploration doesn't have to stop here. The world of materials mechanics is vast and ever-evolving, teeming with opportunities for further study and application. Perhaps you'll apply these concepts in your next project, or maybe they'll spark a new line of inquiry in your studies. The potential is limitless. Remember, the beauty of engineering lies not just in understanding the concepts, but also in applying them to create, innovate, and solve real-world problems. So continue to explore, question, and innovate. If you have enjoyed this video about the mechanics of materials, why not give this video a thumbs up? Your likes guide us in creating content that you love. And if you're new here and you found value in this video, consider joining the family. Hit the subscribe button and the bell icon to ensure you never miss out on a new video.